Good morning, young people. Sorry, yesterday I recorded this and there was too much background noise, so I had to re-record it this morning. So we're talking about mass, temperature, and heat, and we're trying to make sense of it all. So before we make sense of mass, temperature, and heat, I want to take you back for a second to something you're very familiar with. So equations and relationships. Science is full of equations that were developed by looking at experimental data and the relationships among the variables. One that's quite familiar to each of you is this one, Newton's second law, force is equal to mass times acceleration. You used this calculation in Mr. Pritchard's class, but what were the relationships that Isaac Newton saw to help him come up with the equation? How did he develop this? So let's look at that for a second. Force is equal to mass times acceleration. There was an experiment that I used to do when I taught the physics class, and it involved a bendy ruler and a cart and boxes of clay. And what we would do is we would keep the mass the same. So we would keep the mass the same by using just the cart. And then I would take the bendy ruler and I would increase the bend, which meant that I was increasing the force, and that meant the acceleration would increase. When I decreased the bend or decreased the force, then the acceleration would decrease. Okay, so that was one part of it. The next part of it is I added more mass, but I tried to keep the bend the same, so that meant the force I applied was the same. So as mass went up, then the acceleration went down. And as mass went down, the acceleration went up. These are the things that we saw in this experiment. Okay? When acceleration is held constant, and this is a hard one to do in that experiment, but when acceleration is held constant, then we know that as force goes up, mass is going up. If we think about this in terms of a small Fiat versus a semi-truck, if they're both going the same speed or the same acceleration exactly, which one's going to have a greater force? Well, clearly at the same speed or acceleration, the greater force is going to come from the bigger item, the more massive item. So again, if we're talking about mass and force, as the mass goes down, so does the force. So if we're looking at these, what we see is we see relationships. And these were developed by Newton many hundreds of years ago. And he saw the same things that we're seeing today. So if both are moving in the same direction, which when mass is held constant, force and acceleration are, then it must be a direct relationship. And if it must be a direct relationship, that means that force is proportional to acceleration directly. So they're proportional to each other directly. We don't have to do anything with it. Over here, though, we see when force is constant, mass goes up and acceleration goes down. So they are moving in opposite directions, so that must be an indirect relationship because one goes up and the other goes down. Okay, as one goes up and the other goes down, then we have an indirect relationship. By the way, I had some henna done yesterday at the Indian festival downtown, so forgive me. Therefore, we know that mass is proportional to 1 over acceleration. The same is true for acceleration. Acceleration is proportional to 1 over the mass. We're just trying to kind of give it an equation feel, okay? Then if we look at acceleration being constant, we can see that both are moving in the same direction. As force goes up, mass goes up. As force goes down, mass goes down. That's a direct relationship. Therefore, force is proportional to mass. So if we take all this information and we use it, well, I have a triangle here that helps me with that formula of force is equal to mass times acceleration. If I cover up the letter I'm looking for, if I cover up force, for example, I get its mass times acceleration. And what I see with that is that force is going to be directly related to both of those things. And if you notice right here in this proportionality, force is proportional to acceleration, and the one on the far side, that is true. They're directly related. Okay, so now if I cover up mass, I see that that's equal to force divided by acceleration. Well, that is right here. Mass is proportional to 1 over the acceleration. So we can actually see the differences in what we have. And we can also prove that acceleration is the same as the mass proportionality. Acceleration would be proportional to 1 over mass. And so you can kind of see how this equation was put together. So we're going to be trying to use the same thing to develop something of a relationship between mass, temperature, and heat. So the first question that we have here is 2 containers of water are at 20 degrees initially. One container contains 50 milliliters, the other 100. They're each heated with the same source of heat for the same amount of time. If the final temperature of the 50 milliliter sample is 50 degrees Celsius, what would be the final temperature of the 100 milliliter sample? So we start by looking at some information. We know that the initial temperature, sorry, I'm writing with my fingers so it may be a little sloppy, for both beakers is 20. So both beakers are 20. We know the temperature final for the first beaker is 50, but we don't know this one. So I'm going to put an X there because I don't know it. Now, in class we talked about the fact that the time of heating is really about the amount of heat or Q supplied. Since they're heated for the same amount of time, the same amount of heat was applied. So I'm just going to call that Q. All right? And then we know that we have to have a mass relationship here. And we know since the density of water is equal to 1 gram per milliliter, that means that this one with 50 milliliters has 50 grams, and this one with 100 milliliters has 100 grams. Okay? We can clearly see here that Q is constant. So Q is being held constant. Heat is constant. Okay, so heat is constant here. Now we have to figure out some other stuff. So let's start with change in temperature. Remember, change in temperature, just like change in speed or change in distance or change in time from last year, is the final temperature minus the initial temperature. So we get a change of 30 degrees Celsius. Okay, so that makes sense. We have supplied the same amount of energy. So we see that right here that we supplied the same amount of energy to both of those. But we doubled the mass. So I wonder if doubling the mass would be proportional to having the temperature change, because if I have double the mass, the same amount of heat would have half of the change in temperature. So that means that the change in temperature for this guy is 15 degrees Celsius. So that means that the calculation would be 15 is equal to x minus 20. So x would be equal to 35. Okay, so we got that yesterday, and so we kind of started understanding that. So let's see about the relationships. Let's see what we can come up with those relationships. Okay, so question 1, heat is being held constant. As mass goes up, temperature goes down. And as mass goes down, temperature goes up. So we know that they are moving in opposite directions. So that means it's an indirect relationship. Therefore, we have mass is proportional to 1 over the temperature. Very similar to the one where we talk about mass and acceleration. They're moving in opposite directions, indirect relationships, so we have that. All right, let's go on to question number 2. Question number 2, 2 containers each have 50 milliliters of water at 20 degrees initially. They are heated with the same source of heat. One is heated for 10 minutes and the other for 5 minutes. If the container that was heated for 5 minutes has a final temperature of 30 degrees, what would be the final temperature of the other sample? So, once again, let's make our chart. TI, they're both starting out at 20 degrees. 20 degrees. TF, we know that this one goes to 30, and we don't know that one. Q, the heat being added. Well, the one that goes to 30 is heated for 5 minutes, so let's call that Q, and this one is going to be 2Q, okay? Time is what we've got going on here, but we're talking about the heat. Mass. Let's see, they both have 50 milliliters of water, so they're both 50 grams. 50 grams. So clearly, mass is being held constant here. So mass is constant. Sorry, with my finger, the writing gets a little crazy. Okay? So let's go back to our change in temperature thing if we can and see what we've got going on. So the change in temperature for the first beaker that we know the final temperature for was 30 minus 20. So that gives me a change of 10. Okay? So I can see here that I added twice the amount of heat. Well, twice the amount of heat with the same amount should be twice the temperature change. So let's go ahead and double that and say that the temperature change of this guy would be 2 times 10 or 20 degrees Celsius, right? So that meant that 20 is equal to this x number that we don't know minus the initial, which was 20. So x has to be equal to 40 degrees Celsius. Many of you just looked at the final and then went from there, which is why one of the choices was what it was. But 40 degrees Celsius is a great choice for this one. So what do we see in proportionality land? So let's go. Here we go. So question 2. In this case, mass is being held constant. As mass is being held constant, as the heat goes up, the temperature also goes up. And as the heat goes down, the temperature goes down. Notice they're moving in the same direction. So that means direct relationship. So therefore, Q is directly proportional to delta T. Notice we're talking about delta T. We're not just talking about the final temperature. We're talking about the change in the temperature. We want to know about that relationship. And remember, there's something called law of conservation of energy out there. Okay, so here's question number 3. 2 containers of water are at 20 degrees initially. One contains 500 grams of water and is heated by a source for a specified time to a final temperature of 30 degrees. The second container has an unknown amount of water and is heated with the same source to 30 degrees. However, it takes twice as long for the second container to get to this final temperature. How much water is in the second container? So we've been doing kind of the same thing all along. So let's keep it up. T initial, 20 degrees for each of them. Okay, T final. Okay, we know that's 30 degrees for both of them according to this. Well, that means that we know that delta T now is our constant. It is going to always be 10 degrees here according to what we know. And that's pretty interesting that we know that because it tells us what our constant is. We've always kept something constant here. Q. Well, we know one was heated for Q amount of time and one was heated for 2Q amount of time. And then we know about the mass. We know the first one has a mass of 50 grams, but this one we don't know the mass of. So now, what can we do? Well, I know that the delta T's are equal to each other, right? So if I know the delta T's are equal to each other, can't I set this proportionality of Q and mass equal to each other? Because they should equal the same thing, right? So what I'm saying is that Q over 50 should equal 2Q over X. And if I cross multiply, what I get is XQ, or QX, it doesn't really matter, and 100Q. You're saying, Ms. Raines, we've got 2 letters. It's okay, watch what happens. See, Q is going to come out because I'm going to divide both sides by Q. Q is now gone, and I get X is equal to 100 grams. So that means that's the mass of the container. So the other container contains 100 milliliters of water. And that completely kind of makes sense to us if we think about it in terms of what's going on with the heat. If I get the same temperature change and I heat it for twice as long, it should have had twice as much mass. So what's the relationship for question 3? Here we go. Question 3. You don't have to worry about it if my face is covering the question 3. If you can't see that, it's okay. Delta T is constant, okay? So if Q goes up, then mass goes up too, if T is constant. If Q goes down, then mass goes down. So both are moving in the same direction. That means a direct relationship. Therefore, Q is proportional to M. So if we continue with our development of kind of this relationship, remember, this is what we started with, right? We're going back to the force. I'm showing you this slide, okay? So if we're looking at mass, temperature, and heat relationships, we've got these 3 proportionalities. Hang on. This right here looks very similar to the force one. And force was on top when it was related directly with these 2 things. So I wonder if I put Q on top, if that will work. So Q on top, M there, and delta T there. And if you look at that, that makes sense because if I cover up Q, right? If I cover up Q, I get a direct relationship with M and delta T. So that looks pretty good. So now we get that Q is proportional to both M and delta T. So M times delta T is proportional to Q. Everybody understand and make sense of that? If you don't, tomorrow ask some questions, okay? I'm going to stop right here. We're going to start with question 4 in the next video. There will be 2 videos up today. Thank you very much.